Here's a simulation of the fluid flow in this particular pipe. So if we look at the speed of the fluid, notice that it's pretty constant, 1.6 meters per second, all the way through the middle and over here towards the end. But let's see what happens when we change the cross-sectional area. So this is a pipe, so it must have a circular cross-sectional area. So again, the velocity on the far left there is 1.6 meters per second. I'm going to take the pipe and I'm going to change its cross-sectional area over on the far right-hand side here. And let's look to see what happens to the volume flow rate. So it's still 1.6 meters per second over on the far left-hand side here. But as we get closer and closer and finally over to this far right-hand side where the cross-sectional area is smaller, the speed of the fluid is faster. So as we saw in that simulation, when we changed the cross-sectional area of the pipe and made it a smaller cross-section as compared to this cross-section, we got a greater velocity than the previous velocity. Now, the relationship that helps us explain or calculate these exact velocities is the fluid flow continuity equation. The area is in meters squared. The velocity is in meters per second. If we look at what's called the volume flow rate, which is just the area times the velocity, the units there would be meters cubed per second. If it's a pipe, remember the area that we would calculate would be pi r squared. Now, if it's not a pipe and somehow the cross-sectional area is rectangular, that's of course the width times the length. So let's look at an example of an example of a problem that we could solve. So in this particular problem, it says a water pipe having a 2.5 centimeter inside diameter carries water into the basement of a house at a speed of 0.92 meters per second and a pressure of 166 kilopascals. The pipe tapers to 1.1 centimeters and rises to the second floor 7.3 meters above the input point. What is the speed at the second floor? So let's look at how we would draw that. So there we go. This is a pipe. So our cross-sectional area will be circular there and there. We know the velocity is 0.92 meters per second. The diameter is 0.025 and the diameter at the end is 0.011 meters. We want to find what the velocity is at the part of the pipe where it's gotten smaller, the cross-sectional area has gotten smaller. So we start off with the equation, the fluid flow continuity equation, and we want to find these respective areas and velocities, and we're solving for V2. So let's do that. So again, we're solving for areas. So our equation's got to be pi r squared for this first cross-sectional area, and then again pi r squared for the second cross-sectional area, because again they're pipes, so there would be circular cross-sections. The first velocity, v1, which is that velocity there, we're going to plug into that part of the equation, and this is our unknown. We're going to solve for v2. They give us the diameter as being 0.025 meters, so to get the radius, we divide that by 2 and square it. Multiply that times V1, and on the right-hand side of the equation, we've got pi times, once again, the diameter divided by 2 to get the radius, and our unknown is V2. So in solving that problem, we get a velocity of 4.75 meters per second.